Today I want to talk about several models that has been tested as very great models on ImageNet testnet. Alright, first we want to talk about residual network. It is ResNet, more well knownly. Let's talk about why model is more deeper than before. Let's talk about AlexNet. It only has 8 layers and it's quite a ancient model but also very well known. And nowadays we have ResNet. It has more than 100 layers, exceeding 152 layers, and it's quite phenomenal. Let's talk about why is that. Let's look at the graph. The red line is the 56 layer model and the yellow line is the 20 layer model, and it represents the training error. But it's pretty odd because 56 layer model has the error rate higher than the 20 layer one. It's quite odd because actually 20 layer model is actually a subset of a 56 layer model. So the reason why it cannot be deeper, it's like suffer from vanishing or exploding gradient, but by the paper it is solved by normalization layer of batch normalization. So the researcher concludes that it suffers from degradation problem. So he proposed a residual network. So we have our desired mapping hx, and he said have a residual function fx which is quite equal to hx minus x. So we reconstruct the thing and it becomes hx equals to fx plus x. So in the structure, our input is x, and then we have a fx, and then we take this x and add it to this place, and then we use the ReLU function. So the residual network improves the deeper network when networks goes deeper. In before residual network, the higher the network, it performs worst. But after residual network, more layers means more success. As we increasing the layer, also we want to increase the speed. So we propose the bottleneck architecture. It's simply adding a layer, and then in the layer it kind of differs its architecture, and then do the residual. And then these two type of blocks actually perform similar time complexity. The bottleneck architecture increased the speed. For example, the 34 layers and the 50 layer one, its flops, its complexity is like pretty similar. Let's talk about the evaluation, the testing of the residual network. Actually, it looks like it outperforms any other existing models. And then it also have a trend of adding layers, and it performs actually gets better. But also there's a when ResNet exceeds too much layers, it also suffers from the degradation problem. It's quite noticing. Alright, let's introduce MobileNet block. So it's a MB convolution, no block. It is a vanilla convolution. Is it it separately get three channel input and then filters it and get a mapping to it. But in MobileNet, we're using depthwise separable convolution. It's a three channel input and each generate a filter and then each generates a map. By some experiments, they think it performs similar accuracy as the traditional convolution. So they're using this to decrease the time complexity. Actually, it decreased quite a lot. On the left is a residual block that we just mentioned before. And now we want to introduce a inverted residual block. Basically, it's adding channel and then they shrink the channel, and it's proved pretty doing pretty well on MobileNet. And the model architecture of MobileNet is like this: it have a convolution 2D and several bottleneck layers, and a convolution 2D and average pooling, and then another convolutional 1 times 1. And let's talk about scaling method in using compounding coefficient. Scaling is all about three dimensions. It's about width, width scaling, depth scaling, and resolution scaling. Compounding scaling is scaling several dimensions of scaling method simultaneously. Like on the graph is depth and resolutional scaling, and it is represented in the red line. All right. Compounded scaling method is quite simple. It's all about setting several parameters to decide how well the model scale. Like depth is alpha, and width is beta, and resolution is gamma. And it will be times, like depth is times the alpha power 5. And we want that flops, and namely the time complexity, to be similar to 2 of pi. So we want to set alpha times beta power 2 times gamma power 2 is similar to 2, and alpha, beta, and gamma have to be all greater than 1. Let's talk about EfficientNet. Our baseline network is EfficientNet, and it contains several MobileNet convolutional layer, and then doing the pooling and then fully connected. Quite simple. The thing is that how to scale the network. How good EfficientNet is. It is the state of the art on the ImageNet. And also the parameter is greatly reduced. Look at this. It's 60 and then reduced to 7.8. And then it's also the flops, let's say the time complexity is also quite small. And yeah, it's a state of the art compared to another network.